Okay, so we're going to start with Rolle's theorem. So Rolle's theorem says let A just be less than B, any two numbers. Okay, no big deal there. A is less than B. F has to be continuous on a closed interval, A to B. So including A and including B, it's closed. And it's differentiable on the open interval A and B. So it doesn't necessarily have to be differentiable right at A and B. And the other catch is that f of A has to equal f of B. And if that's true, there is a C, some number between A and B, where the derivative equals 0. Okay, so under the hypothesis, what that's saying, if the derivative again is equal to 0, remember we have a horizontal tangent line somewhere, so we had a max or a min somewhere between those. Okay, so let's try that. So I have f of x equals x squared minus 2x squared. This is a polynomial, so I know it's a continuous function. So it has to be continuous on the function negative 2 to 2, and I know it's differentiable. So that part's set. So to verify Rolle's theorem, I have to first show that f of 2 is equal to f of negative 2. Okay, well, let's find each one. So f of 2 is equal to 2 to the 4th minus 2 times 2 squared. 2 to the 4th is 16, minus 2 times 4, which is 8. So I have 16 minus 8 equals 8. Okay? And now I need to verify f of negative 2. Well, that's negative 2 to the 4th, minus 2 times negative 2 squared. So I have 16 minus 2 times 4. I still get 8. Okay, that part of Rolle's theorem holds. That checks. So that means that if I take the derivative, so my derivative f prime of x is equal to 4x cubed minus 4x, that somewhere this thing is equal to 0. There is a value between negative 2 and 2 where that derivative has to equal 0. So we're going to prove that. So 0 equals 4x cubed minus 4x. I'm going to factor out a 4x. I'm left with x squared minus 1. I'm going to keep factoring, so I have 0 equals 4x times x plus 1 times x minus 1, and I get x equals 0, x equals negative 1, and x equals positive 1. So this shows me that there are three values, and notice 0 is between negative 2 and 2, negative 1 is between negative 2 and 2, positive 1 is between negative 2 and 2. So Rolle's theorem holds, and there are three values for which that is true. So we're kind of basically looking at same thing as we did when we did max and mins back in 4.1. We know that we have max or mins at x equals 0, x equals negative 1, and x equals 1, possibly depending on there. But we know the slope hits 0 at those exact points. Okay, so the mean value theorem is kind of an extension from that Rolle's theorem. So again, it starts off the same way, that A has to be less than B. We have two numbers that A is less than B. F is continuous on the closed interval and differentiable on the open interval, means the endpoints don't have to, we're not worried about the endpoints being differentiable in case they're cusps or whatever. And the mean value theorem says we have some C in AB where the slope has to be the same as at two different points. So if I'm looking at this graph, if I have 2 points, here are my endpoints, A and B, there's a slope between them. And so what the mean value theorem says is that for any 2 points between them, as long as there's interval, I have to have another line, some point between them, where the slope is exactly the same as the slope of the line between those two endpoints. So under appropriate smoothness conditions, the slope of the curve at some point between A and B is going to be the same as the slope adjoining those two endpoints. So if I just took A and B and drew a straight line, there's at least one more point on the curve that would have that same slope. That is what the mean value theorem is telling me. Okay, so in this one we want to determine all the numbers C which satisfy the conclusions of the mean value theorem for the function. So we're given f of x equals x cubed plus 2x squared minus x on the closed interval negative 1 to 2. So in order to use mean value theorem, we've got a couple of things to check. First, is f of x continuous? Well, it's a polynomial function, so we know it's continuous. And we also know that it's differentiable on the whole interval. So we've got that checked, we've got that checked. So in order to figure these out, the first thing we need to do is evaluate the function at our a and our b. So in this case, the negative 1 is like the a, the b is the 2. So I'm going to first find f of 2. So that's just 2 to the 3rd plus 2 times 2 squared minus 2. So f of 2 is equal to 14. And I'm going to find f of negative 1. So that's negative 1 to the third plus 2 times negative 1 squared minus negative 1, and I get positive 2. Okay, so f prime of x, also need to calculate that, is equal to 3x squared plus 4x minus 1. So the mean value theorem tells me that somewhere I have f prime of c is going to equal f of b, so f of 2, minus my f of negative 1, all over 2 minus negative 1. So plugging in what I know, I have f prime of c equals 14 minus 2 over 2 plus 1. So I have 12 over 3, which equals 4. So it's saying somewhere this derivative equals 4. So I'm going to plug that in. So I want to know, when does 4 equal 3c squared plus 4c minus 1, right? I'm trying to find, that looks like a 7 up there. I'm trying to find what c values make this work. So I'm going to make it equal to 0. So I have 3c squared plus 4c minus 5. And then I need to solve this. Okay, so it multiplies to 15 and it has to factor to 4. Okay, so I don't think I can factor that, so if I'm not sure, I'm just going to use the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So I have x equals negative 4 plus or minus the square root of 4 squared minus 4 times 3 times negative 5 all over 2 times 3. So I have x equals negative 4 plus or minus the square root. 4 squared is 16. Negative times a negative is positive. 4 times 3 is 12. 12 times 5 is 60. All over 6. So I have negative 4 plus or minus the square root of 76 divided by 6. Okay, so simplifying, and I'm going to skip a couple of steps here. That factors to negative 4 plus or minus the 76 breaks down to 4 times 19, so I can pull out a 2, and then I pull out a GCF, so just because I'm running out of room. So this turned into negative 2 plus or minus the square root of 19 over 3. And that gives me 2 approximate answers when I go to my calculator. If I do negative 2 plus radical 19 and divide by 3, I get approximately 0.786. If I do negative 2 minus radical 19 over 3, I get approximately negative 2.11. Now we had to be in the interval negative 1 to 2, so that's why I'm not including this. So my c value is equal to that 0.786. So we found a value within our closed interval that holds for the mean value theorem. Okay, so I want to make sure we have a better understanding of this. So on this graph, I want to find all the points on the graph at which the slope of the tangent line equals the average rate of change of the function over my interval a to b. Well, notice from a to b, I think I can draw a line here, I'm not sure. We'll see. A to b, so here's the endpoint A, here's endpoint B. So if I draw my line, oop, nope, that didn't work. Okay, so I was able to draw the arrow. Let's see if I can make it a line, not an arrow. Okay, so I'm drawing a line to connect those two endpoints. So that's the slope of the line. So now what I want to know, is there any way on here where I can have the same exact slope? That's what we're talking about. So if I move this, right, I'm just shifting it, I can see that right here, I'm going to have one at right around C. And as I continue this, I'm looking for where it might be exactly tangent, and it looks like it's tangent right here at about D again, and then nowhere else. So we're looking for where on the graph does the slope of the tangent line match the slope between the endpoints. That's basically what we're looking for. And so this is not quite at the maximum because it's just a little bit off. This isn't quite at the minimum, it's just a little bit off to be able to get those. So we have two values, one at C and one at D, they're both between A and B, that my derivative, my slope of that line, was the same as the slope between the endpoints. All right, so let's try another one of these graphical ones, because the graphic ones I think help us understand that mean value theorem a little bit better. So again, we want to know all the points on the graph where the slope on the tangent line is going to equal the average rate of change between my endpoints. So my endpoints are -4, so right here, and +2. So there's my straight line. It's a little bit off. Let me move it down just a little bit. Looks a little bit better. So I'm looking for any place on the curve that has a slope that is roughly the same as that. Well, excuse me, roughly. By roughly, I mean in my drawing. Everything else is going to be exactly the same. So let me just draw another one. So there's my parallel line. And I want to move this around, right? We can see I matched them pretty well. Where on this curve, as I move this, do I get tangent to my curve? Well, right about there I get there. So let's mark that. Right about here, it's tangent. And then as I keep moving my curve, oh, it took my point with me, man. So now as I'm taking this and I keep moving, I see that it happens right about over here again. So I have two values. So this first one, whoop, losing my whole grid. We said it happens right about here, so not quite at -2. And then we said as we kept moving this line and we wanted to know where it was tangent again, it's right over here a little bit after 1, so maybe at 1.25 is where the graph has the same slope. So that's all we're talking about with the mean value theorem, that the slope between 2 points on the line, we're going to have another point between them that will match that slope. And we said it was right about there. And we had one more over here. So the slopes have to repeat.